5.4, mutually exclusive events. Now, let's recall a definition that we took down quite some time ago. If you don't remember, don't feel bad. We'll revisit it right now. So, mutually exclusive events are two or more events that cannot occur at the same time. So an example of this is sunrise and sunset. Or if you are rolling a single die, getting a 2 and a 4 at the same time. Because when you're rolling a single die, you can only see one face. So you can even extend that, saying you cannot roll a 2, a 1, or a 5. So that's more than two events that cannot occur at the same time. So if we're thinking about this in terms of event diagram, that means that there's no intersection. So when we're developing a formula for events that are mutually exclusive, we're going to use something that looks a little bit familiar. So let's move on quickly to this first example. Jamie claims that the probability of A union B equals the probability of A plus the probability of B, where A and B represent mutually exclusive events. So that means if we were to draw a Venn diagram here, we would have A and we would have B. There would be no intersection between these. So let's see if she's correct. Now I'm going to kind of develop a little bit of a formula here. So if you're not quite following everything here, don't worry so much. But if you kind of like math formulas and stuff like that, hang along for the ride. So Jamie reasons that the probability of A union B would be the same thing of number of elements in A union B over the number in the universal set. Remember, this is just our theoretical definition that we took down a couple of days ago. So if they're mutually exclusive, that means that there's no intersection between them. So that means, if we're assuming that, we're saying the number in A, or the number of favorable outcomes in A, plus the number of favorable outcomes in B, still all over the number of elements in the universal set. We can separate these out using our sweet fraction skills. Number of favorable outcomes of A over the number of the number of number of elements in the universal set plus the number of elements in B, or favorable outcomes of B, over the number of elements in the universal set. This, going back to our definition of what theoretical probability states, is that's the probability of A plus the probability of B. So you're noticing that the same sort of notation that we used in the last unit, and in the last unit, and maybe even in the unit before when we were talking about set theory, can be applied to probability, and you'll see that in upcoming examples.